Hi, I'm McLoughlin. I'm going to talk to you about fuzzing and a crypto vulnerability. So anyone who's spoken to me about Go recently knows I'm concerned about the sheer number of lines of assembly in Go's crypto. There's over 8,000 lines of x86 assembly in the standard library, over 10,000 lines in X crypto. And you might choose to panic about this. You might also remember that we have one of the world's foremost experts maintaining Go's crypto, so everything's okay, but we can also help by testing it ourselves. And fuzzing is a great technique for this kind of thing. It's an automated testing technique for hardening safety-critical software, usually used where your software handles untrusted inputs, where correctness is paramount, so parsers, network protocols, and cryptography are common. GoFuzz is the standard solution for the Go community, and the way you do it is you provide a fuzz function that takes arbitrary bytes as input and returns a status code, or it might panic. So the most simple example is just calling your function, and when you run it through the fuzzer, it's going to do everything it can to try and make it crash. It's going to hit your target function with cleverly constructed random data. It's going to build it using instrumentation and guide the fuzzing through that instrumentation. And in this talk, I'm going to focus on differential fuzzing, which compares your implementation against a reference implementation and looks for mismatches. Hence, CryptoFuzz was born, which was an attempt to apply GoFuzz to Go's crypto. And all it does is it takes the pure Go implementation of an algorithm, runs it against the data, runs the assembly version, and crashes if there's a mismatch. So first, for the good news, almost everything passed in crypto, also in X crypto. There was a small mismatch in the Curve 25519 implementation, but it didn't have any security implications. But there was one problem in an algorithm called Salsa 20. After about 20 seconds of fuzzing, it found a crasher, and this was the data that made it crash. So to understand this, we're going to have to understand Salsa 20, and this is where things get hardcore. Salsa 20 is a stream cipher. What that means is it takes a stream of plaintext bytes, it produces a key stream, it bitwise XORs it into the plaintext to produce the ciphertext. And we're going to focus on the key stream that Salsa 20 produces. It does so in blocks of 64 bytes, controlled by an incrementing 64-bit counter, which is also combined with the key material. So as the counter increments, it produces 64 bytes of the key stream at a time, and so on. So now we're in a situation to understand a bit more about what about this input caused a mismatch. And after a load of experimentation, I realized that the important things here are that this bug would be triggered when the high 32 bits of the counter are non-zero, and when the plaintext being encrypted was at least 256 bytes. So when I was digging around this assembly file, that allowed me to hone in to this label called bytes at least 64, and the code following it, which contains 4 lots of a counter increment code. So let's zoom and enhance to these 7 lines of assembly. What's happening here is this is incrementing a 64-bit counter, but it's doing so in 2 32-bit halves in the DX and CX registers. We'll actually step through this, and this is incrementing the counter that consists of all 1s in the low 32 bits, so it's going to overflow into the high 32 bits. And watch what happens. So we increment the low 32 bits that's in DX. We shift the high 32 bits into position. We add the high 32 bits into the low 32 bits. We do a move. We shift the high 32 bits down again. And then we store the low bits in memory, and we store the high bits in memory. So to be clear, actually everything so far is fine. This has taken the counter and it's correctly added 1 to it. The problem happens when you repeat this. So we go through it again. We're going to increment the low 32 bits. We're going to shift the high bits into position. And now this, right now, is where the bug happens. If you watch this, in the DX register, we have a 2 in the high 32 bits, and that is wrong. So what's happened is that the high 32 bits was not cleared. And by repeating this, we end up adding the high 32 bits into itself, thereby doubling it. So if we just continue this, what I'm going to do now is just go through the entire 7 instructions over and over again and watch the high 32 bits. Goes from 2 to 4, from 4 to 8, from 8 to hex 10, hex 20. And that's the bug. So this counter update doubles the high 32 bits. Why is there music? So the counter update incorrectly doubles the high 32 bits. And this is going to have the effect that when we carry into the high 32 bits for the first time and get that 1 bit in there, by doubling it every time, actually we're going to shift that 1 bit out of the 32 bits, like within 32 steps. So actually the high 32 bits is very quickly going to become 0, which actually means that this counter value is going to cycle back to the beginning, and that has the effect of the key stream cycling back to the beginning way sooner than it was supposed to. And I verified this by getting a massive EC2 instance and encrypting 256 gigabytes and observing that this in fact happens. And this bug actually isn't entirely Go's fault. Go version was ported from Supercop and NACL, and the bug was also present in those upstreams. So when you have a bug, you have to disclose it via security@golang.org. And a patch was released within a few weeks after a good attempt was made by Filippo and myself to disclose this to the upstream libraries. It was released on Twitter and through the mailing lists, and it received a surprisingly aggressive response from the upstreams, who deemed this to be not documented use of the algorithm, and it still has not been fixed. So thank you very much. I hope this gives you an idea of crypto and fuzzing. Thanks to Filippo and Adam Langley for handling this so elegantly. And thank you to fuzzbuzz.io for offering free compute to run these fuzzers and helping make Go more secure.